We have incomplete data from two coins, one copper and one silver. The copper coin has probability P1 of landing heads. The silver coin has probability P2 of landing heads. The vector x is given as 100 tosses where one coin is selected at random and tossed. The vector x will record 1 if the coin landed heads. We do not know which coin was used in each toss. Let big Z be the vector indicating which coin was used, 1 for copper, 0 for silver. We will use the expectation maximization algorithm to estimate P1, P2, and pi. Since we are not given the probability of each coin being selected, we will use the EM to estimate pi as a probability copper is selected. 1 minus pi is silver selected. I will sometimes use the NATO phonetic alphabet to avoid confusion. The two-coin EM problem follows this format. Randomly pick a coin with probability pi. Flip the coin Mike times before reselection. We will be solving for Mike equals 1 since multiple flips was not specified. Repeat selection and Mike flips November times. Here November is 100 to match our given data assuming Mike is 1. Find the maximum likelihood estimate for pi, P1, and P2. Here is a table of what our problem looks like. Z sub I is coin selection. X sub ij is recorded outcome. X sub I dot is row sum. Suppose we have the complete data. The probability mass function is the probability x joint z given theta. Since x and z is a vector of only ones and zeros, we can use binomial formula. Probability of selecting copper coin times the probability of heads for copper coin to the power of the outcome, which is our indicator 1 for head and 0 for tail, times probability tails raised to the indicator for tail. If x sub ij is 1, meaning selected coin was head, 1 minus 1 equals 0, we did not get tail. If x sub ij is 0, meaning selected coin was head, 1 minus 0 equals 1, we did get tails. We raise our expression to power of z sub I, so it becomes the joint probability copper was selected and head or tail was observed from the copper coin. We multiply this with the joint probability silver was selected and head or tails was observed from the silver coin. To get the likelihood of PMF of complete data, we take the product of all data. In our product notation, we index all November rows by I and index all Mike columns by J. We expand our rows to be used in our expectation step and convert to log likelihood so we can solve for the maximum likelihood estimates. If we have all the information, these are our maximum likelihood estimates. Z sub I and X sub I are constants with respect to the parameters we want to maximize. Estimated probability of selecting copper coin is the proportion of time copper coin was selected, denoted by the indicator function divided by total selections. If we knew which coin was flipped, then the estimated probability of heads for copper coin is the number of observed heads from the copper coin divided by number of flips before the coin was reselected, summed across all rows. If we knew which coin was flipped, then the estimated probability of heads for silver coin is number of observed heads if silver coin was selected, heads divided by number of flips before coin was reselected, summed across all rows. Understanding how our complete data looks like, we will discuss our data when Z, which coin was selected, is unknown. The EM algorithm notation used will be super T for current estimate and T plus 1 for updated estimate. Posterior probability using Bayes' rule is the probability mass function of missing data. Density Z given row observations joint theta can be written as joint probability of coin selection and row observations given theta over the marginal of row observations given theta. The denominator is our sample space. Z can only be 1 or 0, which we will index using K. We have normalized our likelihood function. Any normalized likelihood function can be used as a PDF since it integrates to 1 and is never negative. Now we have a PMF that we can use in our expectation step. We want to estimate which sequence is from which coin and account for our uncertainty. This is done by taking expectation, which weighs the possibilities by the probability. Expectation of Z sub I given X and theta T is the sum of each Z times PMF. This is the sum over all possible combinations of all completions of the data. We use this expectation to define Z sub I at T. What is the Q function and how is it related to our likelihood? Suppose we have the complete data, Big Charlie. We can rewrite the likelihood by introducing the joint PDF of X and complete, and then integrating out little Charlie. X is redundant when complete is known. Introduce multiplication by 1. we now have form of expected value, quantity times probability integrated. We can use Jensen's inequality to distribute log into expectation. Rewrite using properties of expected value and logarithm. The h function is called the differential entropy. We do not care about it because it is not a function of theta. If we consider the specific value where theta equals theta hat t, this expectation becomes a constant, and the inequality becomes equality at theta equals theta hat t. By subtracting these two equations, we see that when we improve q function, we will also improve the likelihood function by at least as much. So q is some maximizable function that is always below our likelihood function except when they share theta. At each expectation step, we will maximize q. We have shown that increasing q will also increase likelihood by at least as much. So what we saw for earlier was actually our q function. Maximization step. Choose parameters that maximize the likelihood of observing our data. To convert our complete data MLE to EM algorithm MLE, we replace z sub I with z sub I at t. We put hats on all of our parameters and update them to t plus 1. Now that I have explained what all the variables are, we are now ready to solve for the MLE for each parameter. Take the derivative of log likelihood with respect to pi, set equal to 0, expand the terms, factor out pi hat. All possible coin selections add up to November. Solve for pi hat. We step maximize pi hat using updated z sub I at t. Take the derivative of log likelihood with respect to p1, set equal to 0, expand so we can factor out p1 hat. Solve for p1 hat. We step maximize p1 hat using updated z sub I at t. Take the derivative of log likelihood with respect to p2, set equal to 0, expand so we can factor out p2 hat. Solve for p2 hat. We step maximize p2 hat using updated z sub I at t. Run EM takes in each parameter of theta, observation vector, mic equals 1, and a printer switch. Zt is our q function. We will run 10,000 iterations of EM. Our maximization step consists of using MLE to update each parameter of theta from expectation of z vector at time t. The expectation step consists of copying our updated parameter into our q function to update z vector. Then we have this optional printer. EM algorithm can get stuck at local maxima, so we will run it several times at different starting locations. Notice that if we swap the initial starting value of P1 and P2, the results get swapped. This is because we do not have enough information to determine which probability belongs to silver or copper coin. Results that look very different from the others are discarded as local maximas. I actually ran a whole lot more starting parameters, but a lot of them moved a little before getting stuck. Given our data, EM estimates have quite a bit of variation since our November is 100 and mic is 1. Flipping a coin once before reselection gives us the widest possible likelihood function. A larger mic will narrow and heighten our likelihood function. We then average our results. The estimated probability of selecting coin 1 is about 51% and has estimated probability of about 63% heads. We cannot determine if coin 1 is copper or silver, but we can say the probability of the other coin flipping heads is estimated to be around 46%. We can test our EM algorithm using our own simulated data. For each November, we use random binomial to simulate a coin selection. Then we simulate mic equals 1 coin flip. We save our flip observation and hide the coin selection. The estimation varies quite a bit depending on what seed was used to generate the data when mic equals 1. We pass the average EM estimate result into our sample generator. We run EM using the same starting parameters as before. The average of the results are within about 1%.